So we were sort of introduced to the idea of a limit in terms of the Newton quotient alone. So we said the limit as h approaches 0. And part of that was we were looking at the secant slopes and making the secant slopes closer and closer and closer together so that we can create a good calculation for the slope of the tangent. So that was the idea of a limit in terms of the Newton quotient. We can also calculate limits of any functions at any point A in the domain. And essentially, it's just the value that the function approaches. That's the idea of a limit. What value is being approached? So we call it like the argument. So what value is the value that the argument, that the function approaches as its argument approaches A. That's what we call it, argument. The concept is sort of fundamental to calculus as we were using in the Newton quotient. And when we say the word the argument, we're talking about the input, and that's basically going to be the x coordinate, right? That's the independent variable. So if I'm saying x approaches 1, the argument, that's the argument, right? It's the input. Y is the output, right? Sarwa? That's a good question. Research that and get back to me. I don't know. That's just what they call it. Okay, so let's take a look. We have a graph over here. This is going to be the graph of f at x. This is both pieces of this are f at x. And I want to find the limit as x approaches 1. That means, essentially, what does y approach as x approaches 1? Okay, so in plain English, I would be saying, what does y approach as x, the argument, approaches 1? Or sorry, I should write that in English. As x approaches 1. Okay, so here's where x equals 1, right here. And I want to sort of look at this from both sides. So as I approach 1 from both sides, what is the y coordinate approaching here? 0. So the limit is equal to 0. Perfect. Okay, how about negative 2? Here's negative 2. So if we approach this on our graph from both sides, what is y approaching as x approaches negative 2? Yep, so 3. Okay, so we've got that down. It's pretty straightforward. Just what is the y approaching as the x approaches that specific value? Now we have this. We've got this little plus. And when you see that, it looks kind of like an exponent. It's not really an exponent. We can't have an exponent of a plus or a minus. But it is a notation when we evaluate limits. And the plus means from the right. The negative, if you saw a negative up in the exponent area as a superscript, that would mean from the left. Okay? So x approaches 0 from the right. Okay, and we know that because of this. So that means it approaches from the right. Okay, so here's 0 right here. If I'm approaching from the right, I'm going from the right toward the left. And that's the only side that I'm really interested in here. Now, it doesn't really make a difference because this is approaching the same thing from the left and from the right. But it could make a difference if I'm approaching different things from the left and from the right. So as I go from the right towards 0, what is y approaching here? Negative 0.5, yeah. Good. Now that just so happens to be the same as the from the left value as well, right? They're both approaching the same thing. But let's take a look at another example. What happens if I'm trying to find the limit as x approaches negative 1 from the left and then from the right. So from the left, as we approach -1, we're going from the left toward the right. What is being approached? 2. What if I come from the right now toward the left? What is being approached? I'm approaching a y value of -1. So in this case, what I'm approaching from the left and from the right is different. So if I were trying to find what the limit is as I approach -1, if I'm approaching something different from both sides, I can't really decide between that, right? Because the limit is different for each side that I'm coming at it toward. So I actually would say that this does not exist. Okay? A limit can only exist if it approaches the same thing from the left as it does from the right. Okay? Again, important step in your journey to figuring out why the limit does not exist, right? Keaton?
But D and E don't approach the same thing from the left and from the right, so it shouldn't
Right.
exist.
No, they each approach something, right? The left limit exists, the right limit exists. It goes toward a value. But I couldn't say altogether the limit at -1 exists. Okay, so in order for a limit to exist, the left and right limits need to be approaching the same thing. If they're not, the limit cannot exist. Okay, so that leads us to the conditions for a limit to exist, which is the right limit exists, the left limit exists, and also the left and right limits must be equal. Okay? If they're not, then the limit as x approaches a, we would just say dne or does not exist. Okay, so that's with a graph. We can look pretty easily on a graph and see what the limit is approaching. Let's talk about equations. So when I'm trying to evaluate limits, as we did in the Newton quotient, eventually we subbed in h is approaching 0 by subbing in 0 for h, right? Most of the time when we use the Newton quotient, or basically all of the time when we use, almost all of the time when we use the Newton quotient, we have to do a little bit of math work before we're able to sub in h equals 0. Sometimes though, if it's just like a limit of a regular function, sometimes we can try substitution and it might give us out a value, and then that is just our calculation of the limit. So we always try substituting in the value first, so try substitution first. If that doesn't work, if you get the indeterminate form or you get something over 0, then you'll have to look a little bit deeper into it. Okay, so if I try to evaluate part A, if we try substitution, I drop the limit notation as soon as I substitute. And then we just calculate, right? So we'll do 1 squared times 3. That's going to be 3 minus 7 is -4. This is a fine answer. If we get a regular number, that's what the limit is equal to, and that's good, okay? So this one's good. The limit as x approaches -1 is -4 for this function. Okay, let's try substitution for part B here. I'm going to substitute x equals 0 in for both x's. Drop the limit notation when you substitute. And then I'm getting 4 plus 0 and 1 minus 0. Is this an acceptable answer? It's just like a regular number? Okay, that's fine then. So we're good when we substitute. Okay, I'm going to make a little note. Drop limit notation once you've substituted. Okay, here's an interesting one. The limit as x approaches infinity. Infinity is not a number. So it's going to be kind of hard for me to sub in using substitution to try and calculate this. I can, however, sort of look and see what value is being approached as I sub in larger and larger numbers for x. So let's suppose we choose 10,000, okay? So we're going to try subbing in large numbers for x. Okay, so let's do it where x equals 10,000. My function is going to be equal to 3 times 10,000 plus 5 over 2 times 10,000 minus 1. What do we get? 0.5, exactly. Okay, 00250. Okay, let's try an even larger number. Let's suppose we sub in 1 million. 6 zeros. Okay, let's calculate that. $1.5? Is this 0.5, Emma, or did you say 1.5? Okay, let's try this. Okay, 1.5.
Yeah.
Okay,
I got that as well.
and what about this one?
Same thing.
Exactly the same?
3 zeros instead of 2 zeros.
Okay,
325.
325, and this one was 25. So we can sort of guess here what's going to happen. The more zeros I add onto this is going to keep getting zeros in here. And what is being approached? What does this keep getting closer to as we? 1.5. So I'm going to say that this limit is 1.5. Yep, Keaton?
Actually, no. I was going to say limit approaching 1.6 because the number's getting further away from 1.5.
So I would say it's getting closer to 1.5 because we're getting smaller and smaller decimals, right?
Yeah, that's what I meant.
Yeah. So where do you see 1.5 in this equation? Because there's actually a quick way to do these ones when you have expressions like this, linear over linear. Where do you see 1.5 buried in this equation? Three over 2 is actually equal to 1.5. So let me show you guys what's actually mathematically happening here with this graph of this function. This is called, this is a linear over linear function. It's a rational function. But let's look at graphically what's going on. Minus 5 or plus 5? Plus 5? Okay. So I'm asked, what is x, what is y doing when x approaches infinity, right? So when x approaches infinity, I'm going all the way to the right. And when x approaches infinity, it's actually getting closer and closer and closer to what is the horizontal asymptote of this function. So you guys see how there's a horizontal asymptote. I'm just going to put them in as equations here. See how there's a horizontal asymptote here where my graph is sort of curving around? There's also a vertical asymptote as well, right, at half, positive half. Okay, so there's the horizontal and vertical asymptotes of this function. As x goes further and further and further toward infinity, it gets infinitely close to the horizontal asymptote. Okay, that's the nature of asymptotes, right? That my graph is like getting super close to them. It doesn't necessarily touch that value, but that is the limit value, right? That's the limit as we approach that particular y value when x is approaching infinity. So that's what's going on here. X is going toward infinity, and it's approaching the y, which is the horizontal asymptote of this function. Okay? So if you ever see something in this format, okay, it must be linear over linear for this to work. You will take the coefficients of the x's, and that will actually be your limit. This works for if x is approaching infinity or if x is approaching negative infinity. Okay? So this is actually the horizontal asymptote value. Okay, so for our next question, if we try substitution, I want to plug in 3 for all the x's here. I would drop the limit notation. And I'm getting 9 minus 6 minus 3, which is 0, over 3 minus 3, which is also 0, 0. This is what we call indeterminate form, right? That means we can't do substitution to start. Does anyone have any ideas as to how I could simplify this expression before we try substitution again? How could I simplify something like this? Sarwa? Yes, I could try to factor. So instead of subbing in, we're going to keep going with the limit as x approaches 3. And we're going to factor. So we need two things that multiply to negative 3 and add to negative 2 for the factoring on the top. And this is easy factoring, so easy trinomial. These can go right into the brackets. And the bottom, there's not too much we can do with that, but just consider it like a full group, right? So what do you guys see that we can do now? So let's cancel the x minus 3's. And now we'll try substituting again. As long as we don't get an indeterminate form or something that doesn't make sense, we can do it. Is this okay? If I get a regular number, that's fine, right? So I can't do this because it gives me indeterminate form. We can't substitute right away. We have to simplify a little bit first, just like we do in our Newton quotient, and then we can sub in for the limit. Okay, notice as well, as soon as I subbed in the limit here, I dropped the limit notation. But I still had it here and here because I hadn't subbed in x equals 3 yet. Okay, any questions so far, guys? Okay, last part. So some limits are actually going to tend toward what we call unbounded values. And this can happen if we have, like, for instance, a vertical asymptote. And I have this function, just like the one we just looked at. If I'm going toward the vertical asymptote, my x's will go either up toward infinity forever, or they'll approach negative infinity, or my y's rather. Right? They'll approach infinity or negative infinity. So in these cases, so I can actually see the vertical asymptote here. Remember, guys, we find the vertical asymptote where the function is undefined, right, on the bottom. So what causes the bottom to be 0 of this function? 1. So look at what's being approached. 1 is being approached. That's an undefined value for my function. It's a vertical asymptote. So I know this is also a linear over linear function, so I know it's going to have sort of like that same the two curves on either side of my asymptotes. And I know either as I approach this from the left, I'm either going to go up toward infinity on this side, or maybe I go down toward negative infinity. So we have to sort of figure out what that is. So if we try substitution, and I plug in 1 here and here, I'm going to get 4 over 0. Okay? This implies that our limit does not exist. Okay? When I get, of course we know 4 over 0 is an undefined value, right? We know that's not possible. So this is going to imply that our limit does not exist. And the graph has a vertical asymptote, as we said. So firstly, I know there's a vertical asymptote because the bottom was 0 when I plugged in that value. So anytime you get just the bottom equal to 0, that's when you have a vertical asymptote when you're dealing with a rational function like that. Yep. So any value that could make your denominator 0 causes a vertical asymptote, as long as your function's fully simplified. Okay, or it will cause like an undefined point in the graph. That's possible too if it gets canceled out. Okay, so rather than, like we know that this limit doesn't exist. Of course, one side is going to go up and the other side will go down, or vice versa. But we can still calculate the limit as I go toward from the left or from the right. I'm just going to do it with a chart. So let's say we want to approach the value 1 from the left. So let's look at a number line here. If I'm approaching the value of 1 from the left, let's say this is 0, right? I want to start approaching this from 0. So maybe we can start with 0. When x equals 0, we'll sub in 0 into our equation, and we'll get negative 3. Now I want to move a little bit closer to 1 from the left. So perhaps we try, I don't know, 0.5. Okay, we're going to try that out in our function here. Okay, I'll need a couple of people calculating here. Okay, make sure you guys put brackets around these if you're going to do this all in your calculator at once. Farrell, what'd you get? Negative 7. Okay, everyone else, yeah? Someone else confirm this? Okay. Just want to make sure we're getting the right things. Okay, let's move even closer. Maybe we go 0.75. Okay, someone else confirm for us? You got the same thing? Okay. Even closer now, let's go 0.9 and see what we get for that. Okay, negative 39. Okay, I want to go even closer now, like really, really close from the left. Let's say we try 0.999. Did you get the same thing, Clayton? Okay. If I were to keep going here, what do we notice about the trend that's happening here? It's not converging toward any single number, right? But if I were to add a couple more 9s on the end of this, what do you guys suppose might happen based on what you see in the chart here? Para? The number will keep getting larger, but in the negative direction, right? So I'll just keep getting a bigger and bigger negative number. So I can probably conclude that as my graph approaches the asymptote, this left side is going down toward negative infinity. So we'll say negative infinity for that one. The right side is going to go up toward positive infinity, right? Because we have that hyperbolic shape where we have the asymptotes and the two curves that are diagonal from one another. So I will say negative infinity. If you're not sure, based on this, you can always go 0.99999 and see what you get. And then it's just going to give you an even bigger negative number. It'll keep getting larger and larger and larger. or technically smaller and smaller and smaller, because large negative numbers are small. Okay, any questions on this one? Okay. We can do limits of sequences of numbers. Again, a limit is just a value that's being approached. So, sorry, I thought that was the last example. I forgot that there was one more page. I know I said that was the last one, but these are the last ones. So value that's being approached. So imagine if this sequence of numbers were to continue. 0.1, 0.2, 0.3, and so on. 0.6, 0.7, 0.8, 0.9, 1, 1.1, 1.2, and so on. Is this approaching any specific value? No, it's not approaching any specific value. We could say the limit approaches infinity, but infinity is not a specific value, right? So technically this limit does not exist. It doesn't approach any specific value. So this, I would say the limit, we could say infinity, but really we're saying, if we say infinity, we're saying it doesn't really exist, because if it's going toward infinity, then it's not actually approaching any specific value, right?
Did you say that for the last one now? If it's going towards negative infinity?
Yeah, so I said negative infinity.
But that doesn't.
So this is just, yeah, this is just as it goes toward the left, and then as it goes toward the right, it will be infinity, and then it will approach two different things, and it won't exist. But yes, technically, the limit does not exist, right? It can't exist if it's not going toward a particular value. Okay, what about this one? 1, 0.9, 1, 0.99, 1, 0.999, 1, 0.9999, and so on. Is this converging toward one specific value? What do you think? What is it going toward? Yeah, it's getting closer and closer to 1 all the time. Okay, think of it almost like this. If I had like a scale here, and this was like 1 and 0.9, as we go closer each time, we started at 1, and then we went to 0.9, and then we went back up to 1, and then we went back to 0.9, and then we went back up to 1, and then we went to 0.99, and then I went back up to 1, and then I went to 9.999, right? They're all converging toward 1, if you think about it kind of like that. Okay, what about C? So think about this, though. I'm not actually ever going to get to the negatives, right? That's good. Sam? What do you think? It's approaching 0. So I'm getting smaller and smaller and smaller, 1 over 32, 1 over 64, and so on. I'll keep getting smaller and smaller numbers here until I get so close to 0, right? This is kind of the same idea as this, right? If I have 1, and then I go down to a half, if this is, and then I go down to a quarter, and then I go down to an eighth, right? All of these are going to approach. They're going to get super, super close to 0. They may not ever get to 0, but they're approaching 0, right? Okay, last thing is continuity. So we talked briefly in grade 11 about continuous and discontinuous graphs. Or maybe you didn't, but that's okay. If you didn't, then we'll talk about it now. Continuous and discontinuous. Anyone remember the difference between these two things? What makes a function discontinuous or continuous? Bella? Yeah. So if you can drag your pencil along a function, and you can get from one end of the function to the other end of the function without having to lift your pencil, it's continuous. That doesn't necessarily mean it has to go on forever to infinity and negative infinity. It just means I need to be able to get from one spot to the next without having to lift my pen. If I have to lift my pen and jump over to get to another part of the function, it's not continuous anymore. So for instance, if we look at this guy here, continuous or discontinuous? Okay, so as I trace along this, I literally have to take my pen and lift it up to get to this other section of the graph, so discontinuous, right? Okay, so now that we remember what that is, there are 3 conditions for a function to be continuous at a specific x value, and it's these 3 things. F evaluated at that x value must be a defined value, so it can't be something like 4 over 0, right, or 0 over 0, that's indeterminate and undefined. So must be defined at that value. The limit as I approach that value must exist. And the limit and the value of my function must be the same. So the limit's value and the value when I evaluate my function at that specific value have to be the same. Okay, so let me give you some samples here. And also we need to remember here that for the limit to exist, what has to be true? For any limit to exist, what are the conditions that need to be met? They're in a similar box to this above earlier in your lesson. Kenzie? Left and right limits must be equal. Good. Okay, so as soon as I see a left and right limit that are not equal, the limit does not exist, and therefore the function cannot be continuous at that point. So, firstly, are the left and right limits equal? So we can say the limit as x approaches 2 of f at x is equal to 3. Then I would also need f at 2 to equal the same value as the limit. Is f at 2 equal to the same value as my limit? Well, the limit is equal to 3, and f at 2 is equal to 4. Okay, so this is not equal to f at 2. Therefore, the graph is discontinuous when x equals 2. If f at 2 were equal to 3, then I would say this is continuous at this point. Okay, so we know the limit exists, and we know the limit is equal to 3. So this is asking us about what about the limit, and what about continuity? And maybe we can just say the limit exists and is equal to 3. Okay, how about the next one? We have a right. The limit as x approaches 1 from the right is -5. The limit as x approaches 1 from the left is 2. What does this tell us about the limit? Keaton? Yep, so the limit as x approaches 1 of f at x does not exist. And as soon as the limit does not exist, one of the conditions for continuity is broken. So this also means as soon as the limit doesn't exist, my graph is not continuous at this x value. So there must be a break in my graph at this value. As soon as the limit doesn't exist, it can't be continuous.
That's the same type of thing.
Yeah. So if we wanted like a visual of what's happening here, this is a perfect visual, right? I have 2 different values that are being approached from the right and left, and we can clearly see that that happens because I have a gap in my graph, right? If they're approaching 2 different things, there must be a break in the graph causing that to happen. So the limit doesn't exist. So same kind of idea of what we're talking about here. Okay, last one. What do we know about the limit as x approaches -1 of f at x based on our information above? Does it exist? Does it not exist? Surwa? It exists, and is it equal to, it will be equal to 10. Okay, right and left limit are the same, so that's good. Is it continuous when x equals -1? Is the limit equal to the function evaluated at x equals 1? Okay, so this is equal to the function's value, so we know the limit exists. And the graph is continuous at that point. Yes. So that doesn't necessarily mean it's continuous everywhere. That's a good observation. Well, with this limited information, we wouldn't be able to. We would have to have like an equation or something like that where we could graph and see. All right, guys, so I'm assigning a couple things for today. We're going to do the limits worksheet. And I'm also going to assign the additional questions on the Newton quotient worksheet as well that we didn't do before. Okay? So we've got 15 minutes before our break that we can work on this. You can start with the Newton quotient.